Okay, so let's do a few examples of this variation of principles, basically kind of see how this works in a few examples where we actually know the answer to, so that we can see how it actually pops out, and the answers pop out, and how this actually gives us the right answer. But there will be one more example I have after I'm done with these, but I want to save it until another video, so I'll make another video with this other example, basically because I want to talk a little bit more about the result in that case. But so let's look at the first example. So the first one says that we're going to look in a plane, so flat Euclidean space, so there's no forces or anything acting on our system. And we want to know what is the shortest path between two arbitrary points in point set notation x1 and y1 and x2 and y2. So what is the shortest path in this plane between these 2 points? Right? Now, we know already that the answer to this is simply a straight line. Right? This is the shortest path. So this is our y of x. So what we want to do then is see where this actually comes from and how this actually pops out. So here we're going to assume that this is connected by some other path, so let's call this actually our y is x. So this is the path connecting the 2 points, and we want to find out what is the shortest path between these 2 points. So good, so to determine that, let's say we're looking across here, so let's find the line element across this thing. So in this case we know the line element, so if I kind of blow this up, so my line element is this part, where here I am moving in this direction by an amount of dx, this direction by an amount of dy. So this is going to be my dl, which I'm also going to call ds. So my line element in this case is going to be ds. So by Pythagorean theorem, what I know is that ds is then equal to the square root of dx squared plus dy squared. So this is my ds. So then the total length that I'm going to travel between these 2 points is simply going to be the sum over all these different ds's. So at the end of the day, what I want is the integral of ds, which is the same thing as the integral of the square root of dx squared plus dy squared. Or let's pull out a dx. So it's going to be the same thing then as the integral dx from x1 to x2 of the square root of then 1 plus dy dx quantity squared, which is the same thing as the integral x1 to x2 dx of the square root of 1 plus y prime squared. Okay. So this is our integral. So notice this thing has exactly the same form as j. Right? It was the integral over some function f, which depended on y and y prime. So basically, according to this, our f then is simply the square root of 1 plus y prime squared. Right? So this is our f. So to extremize our function, or in this case to find the minimum, all we then have to do is use our Euler equation onto f here to then determine exactly what the path y should be. So let's do that. So what we know then is that Euler equation says that the partial of f with respect to y minus then d dx, then the partial of f with respect to y prime must be equal to 0. Now here, f doesn't depend explicitly on y, so this derivative then is simply equal to 0. So from here, what I get is that d dx, then the partial of f with respect to y prime, must simply be equal to 0. Well, since this is equal to 0, then that means that this guy must simply be equal to a constant. Right? So this then tells me that the partial of f with respect to y prime must be equal to simply some constant. So we call that simply c. So good. So let's take the partial derivative of this with respect to y prime. So if I do that, then the partial of f with respect to y prime is then going to be equal to 1/2 of then 2 times y prime divided by the square root of 1 plus y prime squared. And that must be equal to the constant c. So let's plug that in. So this becomes 1/2. Actually, the 1/2 is going to cancel. So let's ignore that. So it's going to become what? Y prime divided by 1 plus y prime squared, square rooted, is all equal to c. Well, let's square both sides. So let's get rid of this. 1. So this tells me then that y prime squared must be equal to c squared times 1 plus y prime squared. So let's solve this for y prime. So let's subtract that term. Let's see, how do I want to do that? I suppose it doesn't really matter. Let's keep the c squared positive. So let's subtract this term over here. So this is going to become 1 minus c squared all times y prime squared is equal to c squared, which means y prime squared then must be equal to what? C squared divided by 1 minus c squared, which means y prime is then equal to c divided by the square root of 1 minus c squared, which is simply some constant, which I can call m. So m is simply the slope, so integrating this guy tells me that y then is equal to m times x plus some constant c. So here, this is simply the equation of a straight line. So indeed, the shortest path, which connects 2 points together in a flat plane in Euclidean space, is a straight line, which is something we already knew. But again, it's nice to see that this actually pops out. We actually get the right answer. Good. So our next example is Fermat's principle. I don't know if we talked much about this in 206. But Fermat's principle says that, Fermat's principle says that when light enters something like a dielectric, it follows the path which is extremizing the time. So basically, again, if I have light which is coming in and then strikes some sort of dielectric, then the path at which the light chooses, which is also a straight line, is the path such that the time it takes to go through this dielectric, so let's say this has a length of L to it, is what takes the shortest amount of time. So t is smallest. So it seeks the path which actually then extremizes the time, it takes the shortest amount of time. I think we talked about this in 206, but if not, I apologize. So good. So in this case, what we want to do is extremize the time. So we're going to cut this up into a whole bunch of small time intervals. So in this case, the total time then is equal to the integral over the differential times from the initial time, let's call that 1, to the final time of 2. Well, what do we know? So first of all, if this thing has a dielectric constant, which means that it has an index of refraction. So remember, the index of refraction is equal to the speed of light divided by the speed at which it actually moves through the medium. So this means that the speed at which it moves through the medium is the same thing as the speed of light divided by the index of refraction. The time it takes is simply going to be, since this thing is moving with constant velocity, doesn't have to be, but if it's moving with constant velocity, then in this case, the time it's going to take is simply going to be the distance at which it travels divided by the time. Right? So in this case, we can rewrite this then as the integral of the distance divided by the velocity, which is then equal to the time. And again, we're going to integrate this from the initial position to the final position. Or, using that the velocity is this way, so this is finally the same thing as the integral of the speed of light, times then, from the initial position to the final position, ds then divided by, I'm sorry, I inverted that improperly, so this should be 1 over the speed of light times the index of refraction. So this is the integral that we want to extremize. Now, in general, what's true is that the index of refraction is going to be position dependent. So in a general setting, the index of refraction is going to be both x and y dependent. So basically, this integral, t, which we can also call j, is then going to be equal to 1 over the speed of light, and the integral of n x, y, ds, from the initial position to the final position. Now, in a special case where this dielectric constant is simply constant, basically means there is no position dependence to it at all, then the index of refraction is also going to be constant. So in that case, this is going to be the index of refraction divided by the speed of light, integral from the initial position to the final position, ds, but this is the same thing as in the previous problem. So basically, all this says then is what? Fermat's principle says that for lights going into a dielectric, as long as that dielectric constant is purely a constant, doesn't depend on position, then the index of refraction is constant. So in this case, indeed, this is going to move in a straight line in such a way that it's going to minimize the amount of time. So this is Fermat's principle. So good. So last example we're going to look at. Is something which is known as a brachistochrone, I think is how you pronounce that. But basically, we're going to consider that is a particle moving with a constant force. Right. So here we're going to have a force which is equal to a constant. And this thing is going to move from some initial position, x1, y1, to some final position of x2, y2, where x2, y2 is going to be lower than x1, y1. Right? So basically all that means is if I was plotting here, right, so again this is x, this is y, so let's say this is x1, y1, then x2 is going to be somewhere over here, but y2 is going to be somewhere down here, so this will be my y2. So initially my object is going to start, say, somewhere here, and it's going to move down to this position along some particular path. So this is the path y of x. Now here we're going to assume that the initial velocity of my particle is simply equal to 0. And what we want to do is find the path that allows the particle to accomplish the transit in the least amount of time. So here we want to minimize the time. So this is going to take the shortest amount of time. So good. So first of all, since this thing is moving with constant force, we know that as long as it's a constant force, we have to have then, what, a conservative force. As long as that's a conservative force, then we have a potential energy associated with it. Now, let's assume that my particle starts off at the origin. So let's actually take y1 equal to x1, which is equal to 0. So this thing starts off at the origin. So we're going to move this point to actually this location. And let's assume that at here, then the potential energy is equal to 0. Right? And the way I can say that is that the potential energy is equal to minus the work. So the work in this case is going to be simply equal to minus the force times the distance of x. So since x is equal to 0 at the origin, so in this case, it has no potential energy initially. And let's say that this force is simply causing a constant acceleration, where I'm going to call g equal to the acceleration. Not necessarily this has to be the acceleration due to gravity, it's just some acceleration. So again, what we know is that initially the initial potential energy is simply equal to 0, and we know the initial kinetic energy, sorry, we call that T, is also equal to 0 since this object is not moving initially, which means that the initial energy must also be equal to 0. Now, at some later time, what we also know is that the total energy at some later time is also equal to 0 because there are no non-conservative forces acting in our system, which means that the total energy must be constant at all times. So what this tells me then is that, again, the energy must be equal to the initial energy, which is equal to 0, is equal to the kinetic energy plus the potential energy, which is then equal to 1/2 mv squared minus mgx at any point. So from here we can find the velocity. The velocity then is going to be equal to the square root of 2g times x. So again, our functional j is going to be the same thing as the time, which is then going to be equal to the integral from the origin to some final location. So let's call that simply xy. Then the differential distance, which again is our differential path, divided by the velocity. where our velocity is simply this guy. So it's going to be then ds divided by the square root of 2gx integral 0, 0, x, y. But again, ds is the same thing as that square root. Let's factor out a dx again. So it's going to be the integral from 0 to x dx of then 1 plus y prime squared divided by 2gx square root. So this is then the time that I want to minimize, which means that this is my functional integral. Now again, since this is j, again, this thing must be f. So in our case, f then is equal to the square root of 1 plus y prime squared divided by 2gx. So good. So to extremize this thing, find the path that actually extremizes. What we need to do then is what? Substitute this into Euler Equation. And then simply solve for the path y. Now again, f here has no dependence on y itself, which means that has to be equal to 0. Which means Euler's equation becomes minus d dx, and then partial of f with respect to y prime must equal 0. And again, all that means then is that what? This thing must be equal to a constant. So from here we get the partial of f with respect to y prime must be equal to a constant. And we're going to call that constant 1 over the square root of 2 times a. That's mostly put in there just for make our lives a little bit easier. Okay, we'll talk about what a actually is. So good. So let's plug in f. Let's take derivatives of that with respect to y prime. So if I do that, we're going to get, in this case, then is what? So I get a y prime divided by the square root of x times 1 plus y prime squared is all equal to 1 over the square root of 2 times a. Good. I don't need f anymore. Now from here, again, what we want to do is solve for y prime, so let's square both sides. So we get a y prime squared divided by x times 1 plus y prime squared is then equal to 1 over 2 times a. Solve this for y prime. So again, I'm going to multiply both sides by y prime, bring over a y prime, and then divide through. So ultimately what I get then is that y prime is going to be equal to the square root of x divided by 2 times a minus x. So this is y prime. So finally, all I need to do is integrate this guy to then determine what y is. So let's do that. Now, remember that y prime is the same thing as dy dx. So this is a first order differential equation, which is fully separable, because here, this thing has no y prime or y dependence to it, so I'm simply going to multiply both sides by dx and then integrate. This side is simply going to become y. So we're going to get y then is equal to, so it's going to be the integral dx square root of x divided by 2a minus x. So we want to integrate this guy. So to integrate this guy, we're going to make a change of variables. So let's say x then is equal to a times 1 minus cosine of theta, which means dx then is equal to a times sine of theta d theta. So basically this integral then is going to become a times integral of d theta times then a times 1 minus cosine of theta divided by 2a minus a times 1 minus cosine of theta square rooted times sine of theta d theta. Oops, sorry, I already had that d theta there. So from here, basically what's going to happen is we're going to cancel some terms. Let's factor out the a. Actually, the a is going to cancel, right? So this a here is going to cancel with this a. This is going to become 1 minus 1 plus cosine. So the 1 minus is going to cancel. So it's going to become a 1 plus cosine. Sine, remember you can always write as the square root of 1 minus cosine squared. So ultimately this thing is going to become equal to the integral a d theta 1 minus cosine theta, which then gives me, after doing my integration, a times theta minus sine of theta plus a constant c. Now in this case, since we're iterating from 0 to x, right, in that original integral, what that means is when x is equal to 0, theta also has to be equal to 0. So actually in this case, c is simply equal to 0. So this thing is actually what's known as the parametric equation of a cycloid. So what this says then is that the least amount of time it takes for this particle to go from the origin to some point down here is actually going to be a circle, kind of, which basically means that what you're looking at is a circle. So a cycloid is actually defined as, so think of a point on the rim of a circle, which then has a radius of a. Okay. So initially my circle is going to be, say, here. Right? So this is the point, and then basically what happens is as that circle starts to roll across this axis, that point then at the rim, this point will then follow out this particular path. So again, this is my radius of A. So this thing then is rolling across here. So imagine it's rolling without slipping. So as this thing is rolling, this point then is following this trajectory. So that by the time it gets down here, this is A. So this is at a point of 2A. And then as this thing continues to roll, this thing is going to move in a path such as this. So this is what's called a cycloid. So the path that then minimizes the time for a point which is under a constant force. So again, our force in this direction is pointing in the x direction. So we're pushing it actually this way in the x direction. So this has a constant force. So that constant force we're simply writing as mg. Then as this thing is moving, where it's moving to a point which is lower than the initial point, then this is going to follow the path then of the cycloid, which again, imagine a wheel which starts off here. So initially this point on the rim is starting off here. So this is A. And then this thing is going to start to roll, and as it rolls, this point then is going to move down. So you're following this point on the rim, which is then creating the cycloid. Now, again, we have one more example. That last example I'm going to do in a separate video because I want to point some things out, so it's going to take a little bit of time. I don't want the video to be too long. But again, this is variation of principle. So far we've seen 2 examples that we know the answer is supposed to just a straight line. And of course what pops out is of course that answer of just a straight line. So this is how we know it actually moves in a straight line, is via this variational principles. So we'll do one more video, one more example, because I want to point something out. And then from there we'll talk about what's known as the second form of Euler's equation. But we'll get there.